So then I actually finish this tutorial with the last part, which is more about perspectives. So within some of the developments in the last years on the field, but what is left to do, at least in our opinion. And I think a very important point of self-supervised learning is that nowadays in the era of foundational models, I mean, everything we talked about and the results we've shown were training a neural network from scratch, but nothing in the theory we presented kind of stops us from using it to just fine-tune the a neural network, a pre-trained neural network or a large foundational model. Okay. So we can imagine fine-tuning fusion models and so on, and doing other types of test time training to take into account distribution shift of a specific distribution that we are constructing. Then to give you an idea of this is the problem of distribution shift. Here I trained a neural network, a supervised neural network on zeros and ones of the MNIST data sets on going from single pixel camera measurements, which are highly compressed. So if you look at the measurement, you will not recognize the zeros and the ones. But the neural network does a great job, gives you very good estimates. However, when you test at 2, 3, 4 that the neural network has not seen, you will try to imagine that everything is a 2, a 3, and a 4. But if we now train it on an unsupervised way, or we fine-tune it on an unsupervised way, we can use the 2, 3, 4 measurements even at test time. There is no cheating of using measurement at test time once we are having ground truth. We obtain something that it's very close to the 2, 3, 4. So we kind of reduce this risk of distribution shift. What's about non-linear inverse problems? So we've seen that the model identification theory and most of the results that we've shown work for linear inverse problems where A is a matrix. There are many other realistic problems where it's not the case and A is not linear. So for example, we can imagine just observing a very highly quantized version of measurements. In this case, we took the extreme and said we're only going to observe 1 bit per measurement, so whether it's positive or negative, the sign. And when we do that, just using a standard wavelet-based method will completely fail, and you will not even know what is the distribution about, the IHT. Whereas if you do self-supervised learning, you will have a larger gap, maybe with supervised, but still you'll be able to reconstruct the shapes and realize that those are pictures of clothes. You can also do this for clipped measurements, saturated measurements. For example, CCD cameras have saturation problems. And this is a non-linear inverse problem where you can use also invariance, in this case, to amplitude changes, learn beyond the saturation. So another important question that it's quite open is can we train samplers instead of just estimators? We've been focusing a lot on estimating the posterior mean. But what happens if we now want a posterior sample? So one of the approaches that exist in the literature is the idea of ambient GAN, which trains a GAN, a generative, so trying to learn a generative model for P of X, given just P of Y. And it's similar to what Mike presented in the previous part, where we just try to make sure that the projections of the distribution are consistent with the data. Okay, so we will just push forward a Gaussian through a generator network. We will use a certain P of X, and we will project it down through our different operators and try to impose consistency of distributions. Another family of sampling methods that look promising on this direction is the idea of diffusion models. And as we've seen in the second part, the NMSC estimator for denoising is a 3D formula. So we know that if we observe images at different noise levels, we could leverage 3D formula and self-supervised learning to do diffusion. Okay, because the key can be approximating self-supervised losses. This idea has been extended for incomplete measurements, where we can use some partial measurements observed for different operators. And there's also some works on using variational autoencoders for learning these posterior samplers in a self-supervised way. So another point that we have not touched, but it's actually somehow closely linked to self-supervised learning, is the idea of uncertainty quantification. So when we train our self-supervised network, it will give us some picture, and how sure are we that that's the right answer to our problem or not? Well, the answer is using uncertainty quantification. And the key here is that actually, because we can train a neural network without ground truth data, it somehow means that we know what is the uncertainty. Because in order to train the network, we are telling it where is the error. We kind of know the error without any ground truth. This can be seen, for example, in the Shor losses I presented in the second part. They are unbiased estimators of the noising error. There's also extensions of these Shor type losses for estimating the error of the error, okay, so Shor for Shor. And there's also some work we've done with Marcelo on trying to use equivariance imaging to find uncertainty estimates that are well calibrated. So basically, why this works is very similar to why self-supervised learning works. So beyond images, so can we everything we've seen in this tutorial was about reconstructing images, but all the mathematical tools we used were not specific about images, and we can think about audio, we can think about reconstructing point clouds or graphs and so on. And here the key is to identify which invariances, for example, are applicable to a specific data domain, and what are the noise distributions that we're handling and so on. Another interesting point that is quite open at the moment is the idea that what happens if we just we don't want to only reconstruct, but we want to do some downstream task on the image that we're reconstructing. For example, we want to classify the MRI image that we are just reconstructed. We need less constraints in that case if we're just interested in classification rather than a high-dimensional regression of the image. Can we think of self-supervision in this case? What are the links with self-supervision, more generally computer vision? And finally, so everything we presented generally requires applying operator A during training and backpropagating through it. And this is often hard in very large-scale problems because of just computing the operator A can be very, very expensive. And so there are interesting challenges on how to reduce the cost, the computational cost of doing this self-supervised training. Some of the ideas that are appearing recently are using sketching, trying to in this way. So just to conclude the tutorial, we've seen lots of different ways of doing self-supervised learning for imaging inverse problems. We've seen a theoretical side of what are the necessary and sufficient conditions on the problem for doing the learning, and not just throwing deep learning at it and hoping that it works. It requires some conditions to be met. in order to be possible to do so, we've seen that some of the keys are building unbiased risk estimators of the supervised loss. And we also saw that there's an important interplay between what are the physics, so what is the actual forward operator that we are looking at, and what is the invariance of the data. So invariance to translations, rotations, and so on. And this can give us sharp constraints on the number of measurements we need to observe. So hopefully this theory can help practitioners designing computational imaging systems to come up with effective ways of doing so. And in practice, we've seen that we need to build self-supervised losses to train our neural networks without the ground truth. And most of these losses that we've seen during the tutorial are applicable to any neural network, whether it's a UNet, whether it's an unrolled algorithm, whether it's learned regularization, and so on. And they can be put together and combined together. So there is a lot of space to play around and combine ideas of invariance with ideas of robustness to noise and so on. So to end the tutorial with a meme, we started historically in the 1950s, 60s with linear imaging, just applying the adjoint or the pseudo-inverse operation, which give us some poor reconstructions because they cannot really handle noise or incomplete operators. We moved to regularized imaging with priors like total variation, sparsity, and so on, which improved the reconstructions, but was not really taking into account the data, the distribution mismatch, by that the real images do not look like necessarily like TV total variation images. So we moved to supervised learning and data-driven imaging, which improve the reconstructions even further, but requires ground truth. So it's only applicable to kind of more toy problems and not really applicable to scientific and medical imaging settings. And today we spoke about what we hope is a new way of doing computational imaging, which is measurement-driven imaging, where we learn from the measurements themselves. We can exploit all the data we have without doing assumptions, specific ground truth distribution, and imposing very little prior knowledge like invariance and low dimensionality. So tomorrow will be doing a tutorial on deep inverse, which I think you already know, some of you don't. Andrew in a second will come to give some requirements for tomorrow. And just to say that this is an active project that you can contribute to. So if you like the library and tomorrow's tutorial, please consider contributing, because we go to the beach to go. So, and